In a revelation that stunned the scientific community and captured imaginations worldwide, NASA recently admitted to a breakthrough that sounds more like the stuff of science fiction than scientific reality. They've developed a propulsion system so advanced it could theoretically reach the speed of light. The announcement didn't come with fireworks or a grand unveiling, but with the quiet precision that often accompanies the most earth-shattering truths. The implications, however, are anything but quiet. For decades, light speed has remained the ultimate cosmic speed limit, a barrier that has confined human travel to the slow crawl of chemical rockets and ion drives. This admission suggests that limit may finally be within reach, or even behind us. The roots of this revelation stretch back years, hidden within the research halls of experimental propulsion projects like the EM drive and other exotic concepts. Whispers of warp drives, vacuum fluctuations, and inertial manipulation have floated through NASA white papers and obscure technical journals, often dismissed as fringe theories or long shots. But behind closed doors, it seems a dedicated team of physicists, engineers, and visionaries were chipping away at the impossible. The newly acknowledged technology, cloaked in a veil of secrecy until now, appears to be a form of propulsion that fundamentally alters the relationship between mass, energy, and space-time. A system that doesn't simply move a spacecraft forward, but bends the rules of motion itself. NASA's admission centers on a theoretical framework that has long been explored by physicists, the manipulation of space-time itself to create propulsion. By generating localized distortions in the fabric of space-time, a spacecraft could effectively surf a wave of space, allowing it to travel vast distances without the need for traditional acceleration. This concept, often likened to the Alcubierre drive, had remained purely speculative due to the astronomical energy requirements and the absence of a mechanism to stabilize such a warp bubble. But something has changed. NASA's engineers have apparently found a workaround, a means of warping space-time without consuming infinite energy or collapsing the structure of the ship in the process. At the heart of the development is what's being called the LPD, or Light Propulsion Drive, a device unlike any engine the world has seen. Rather than relying on combustion or electromagnetic propulsion, the LPD reportedly generates a stable bubble of modified spacetime around the craft, compressing space in front and expanding it behind. The result is motion without acceleration. From within the bubble, the craft doesn't move at all. It remains in free fall while the spacetime around it flows, much like a conveyor belt. This has two staggering implications. Not only can the craft potentially achieve effective faster-than-light travel, but it can also do so without subjecting passengers to the crushing forces of acceleration. The ramifications of this technology are profound. First and foremost, the speed of light, nearly 300,000 kilometers per second, has always been considered the ultimate barrier to interstellar travel. To reach even the nearest stars with existing propulsion systems would take tens of thousands of years. But a system capable of reaching or effectively exceeding that speed changes everything. Alpha Centauri, just over 4 light-years away, becomes a destination reachable within a single human lifetime, perhaps even within a few years or months, depending on the exact mechanics and safety constraints of the LPD. Beyond the stars, this technology could revolutionize our understanding of the universe itself. With the ability to travel at or near light speed, humanity gains the tools to conduct deep space exploration at an unprecedented scale. Planets once thought inaccessible become reachable. Entire star systems open up for study. More than that, the nature of time, relativity, and causality must be re-examined. At such speeds, time dilation becomes a significant factor. Time for the traveler slows down relative to those left behind. This could lead to paradoxes and challenges never before faced in real-world engineering. The possibility of human settlement outside our solar system is no longer a fantasy in this new context. With the capacity to cross interstellar distances, colonization of exoplanets becomes a matter of logistics and biology rather than a fundamental limitation of physics. Advanced telescopes have already identified thousands of candidate planets, some in the habitable zones of their stars. If the light propulsion drive can be miniaturized and scaled efficiently, entire flotillas of exploratory ships could begin the search for new homes, carrying life from Earth to the stars. There is also the question of energy, the monumental challenge that previously held back warp drive concepts. NASA's admission hints at a new form of energy generation or manipulation, possibly involving quantum vacuum fluctuations or zero-point energy. These concepts suggest the extraction of usable energy from the very structure of space itself, an inexhaustible and omnipresent source of power. If mastered, this would not only power spacecraft, but could redefine global energy infrastructure, eliminating reliance on fossil fuels, nuclear plants, or even solar panels. Furthermore, the emergence of light-speed propulsion ushers in a new era of strategic power and defense considerations. A civilization capable of near-instantaneous movement across space possesses an unmatched strategic advantage, not just militarily, but economically and diplomatically. Satellites could be deployed across the solar system in moments. Resources from asteroids and distant planets could be mined and returned in record time. Communications could be physically delivered faster than any signal could travel, bypassing the limits of electromagnetic transmission. From a scientific standpoint, the ability to travel at light speed enables experiments and observations that were previously impossible. Astrophysicists could observe distant galaxies up close. Cosmologists could measure the cosmic microwave background from outside our local cluster. Probes could be dispatched to intercept and study interstellar objects like Oumuamua in real time, rather than watching them disappear into the void. Questions about dark matter, dark energy, and the true shape of the universe could finally begin to yield answers. Yet perhaps the most transformative implication lies not in what this technology allows us to do, but in what it forces us to consider. The universe is vast beyond comprehension, and if we have cracked the code to light-speed travel, others may have done so as well. The Fermi paradox, the question of why we haven't encountered alien civilizations, takes on new weight. Are we about to discover a galactic community long hidden simply because we lack the means to see it? Or are we truly alone, the first to breach the void? The societal impact will be no less significant. Humanity's perspective on its place in the cosmos will shift dramatically. The pale blue dot, once an isolated haven adrift in an uncrossable ocean of space, now becomes the starting point of a much broader journey. Philosophies, religions, and worldviews will be challenged and redefined. The notion of home may expand to include entire star systems, and with it, our identity as a species may undergo a profound transformation. Meanwhile, the technical community will face the monumental task of making this technology safe, scalable, and economically viable. Even if the prototype works, translating it into a functioning, mass-producible system will require new materials, new design principles, and likely new branches of physics. Safety protocols for navigating through distorted space-time, shielding against exotic radiation effects, and mitigating relativistic hazards will need to be developed from scratch. Education systems may be reshaped to accommodate this leap. Future generations might grow up studying propulsion mechanics that rely on manipulating the geometry of the universe rather than thrust and fuel. The role of theoretical physics will become ever more central to engineering. Partnerships between academia, government, and industry will be essential in fostering the kind of collaborative environment needed to bring light-speed propulsion into widespread use. Of course, there will be skepticism. Claims of light-speed travel challenge the bedrock of Einsteinian physics. Critics will demand replicable data, peer-reviewed publications, and independent verification. These are reasonable demands and crucial for the integrity of science. Yet the very fact that NASA, a conservative and highly respected institution, has acknowledged the existence of such a breakthrough lends the development enormous credibility. The psychological barrier of light speed has been a defining limit of human aspiration. Breaking it is akin to when early humans first harnessed fire, or when flight ceased to be myth and became reality. It changes what we think is possible. It alters the scale of our ambitions. It invites us, dares us, to imagine futures that once seemed unreachable. From Mars colonies to Dyson spheres, from interstellar diplomacy to cosmic exploration, a light-speed-capable civilization enters a domain that is quite literally without precedent. In the coming years, every facet of this propulsion system will be scrutinized, tested, and debated. But its existence, even if only in early stages, marks a threshold moment. The next century may not be defined by our conquest of space in the way the 20th century was defined by aviation and computing, but by our mastery over the cosmic speed limit. And once that limit falls, everything else becomes a matter of time. Time, which was once our greatest enemy in space, may now become our greatest ally. Distances that once took millennia to cross could shrink to manageable spans. The stars, long twinkling from unreachable heights, may finally become destinations on a map. Human beings, confined for eons to a single planet, now stand on the precipice of a journey that has no boundaries. A voyage not just to other worlds, but to the very edges of knowledge and existence. Lightspeed propulsion is more than a technological triumph. It is a philosophical awakening, a scientific revolution, and perhaps most profoundly, a human milestone. It tells us that the universe is not closed to us, that we were never meant to remain in the cradle of Earth forever, that the future, for all its uncertainty, is not limited by the speed at which we can dream, but by how bravely we pursue those dreams. And with this new development, it seems the dreams are about to catch up with the stars. The revelation of NASA's Lightspeed-capable propulsion system represents a fundamental turning point in human development. But the ripples it will send through every domain of civilization are only beginning to be understood as the technology moves from laboratory prototype to practical application. The scale of transformation it promises is staggering, not just in how we travel, but in how we organize society, conduct science, approach governance, and conceptualize the universe itself. With the curtain pulled back on light-speed feasibility, humanity now stands on the threshold of its next evolutionary leap, not biological, but technological and existential. What follows such an achievement is not merely the excitement of exotic travel. It is the construction of an entirely new infrastructure built to accommodate and leverage the consequences of interstellar mobility. Earth-based infrastructure, long optimized for planetary needs, would need to evolve in scope and ambition. Orbital shipyards, once considered speculative fiction, could become vital nodes of production. Modular spacecraft fitted with light propulsion drives and constructed entirely in orbit might replace traditional rockets. These stations could serve as hubs for new trade routes, scientific missions, or even act as launch points for entire spacefaring civilizations. Logistics would be revolutionized on a scale that dwarfs every previous industrial transformation. Supply chains could span planets and star systems rather than countries. Valuable resources long buried in the gravity wells of distant celestial bodies could be harvested and transported back to Earth or to colonies elsewhere. Elements rare on Earth, such as helium-3 from lunar regolith or exotic metals from asteroid belts, might become as commonplace as copper or silicon, sparking entirely new industries. The material wealth of the cosmos would for the first time be accessible within the span of a corporate fiscal year. With such vast potential, competition among nations and private entities would intensify dramatically. While NASA's development marks